Good evening, everyone. Welcome, friends, to our first stargazing lecture from Caltech Astronomy of 2021. I'm Dr. Cameron Hummels, computational astrophysicist at Caltech, and as always, I will be your MC and host for this evening's event. We've got a really cool event for you tonight. A rough schedule is I'll go through a couple of announcements in the next couple of minutes, and then take you on a kind of virtual tour of what you can see tonight if you have clear skies and a view of the stars and a view of the heavens. And that'll last about 5 minutes or so. And then I will introduce our speaker, Sarah Blunt, who's going to have this awesome discussion of both an exoplanet science result, as well as how that process went into becoming a science headline in the newspaper that you may have seen. And that will be about a 30-minute presentation. And then we'll immediately jump into a Q&A panel that consists of Sarah, myself, and then two other scientists in the department, Amruta Jaodand and Tony Rodríguez, who will be handling your questions. You can ask questions, obviously, about Sarah's talk and exoplanet science, and we'll try and handle any science questions that you have about astronomy or space or astrophysics or what have you. So that will take us all the way for the remainder of the time, about 90 minutes. So feel free to stick around as long as you want, ask as many questions as you want, and we will try and address all of them. So we do these events once a month on a Friday night. Traditionally, they're in person and we have a stargazing component, but obviously that's been more challenging since the pandemic. I am getting a telescope so that we can do these from my back patio and try and see give a live view of what's visible in the sky. That's not really possible tonight because, well, it's raining and it's cloudy. We have an atmospheric river, they call it, coming over the Pacific Ocean and dumping a deluge of rain upon us right now. So it's really good for the ecosystem, but it's not so good for astronomy. And let's see. So yeah, other events. We also have a sister series called Astronomy on Tap, which consists of slightly less formal talks. It's 2 15-minute science talks by different researchers, both at Caltech as well as now, since it's in the pandemic and it's done virtually, I've been getting speakers from all over the United States. Our next one of those will be a week from this coming Monday, on Monday, February 8th at 7:30 p.m. And yeah, like I said, two informal talks about science topics, and then drinking is encouraged both by the members of the panel as well as yourselves. And then we do astronomy themed pub trivia at the end, which is super fun too. So we encourage you guys to check that out. I haven't yet posted the video in YouTube, but I will soon, and we'll of course put it on our social media outlets as well. So stay tuned for that. And I guess those are the major announcements that I have. Hopefully everybody's doing reasonably well. I have this that's really cool. Some secret admirer left this sweet NASA mask on my mailbox. I have no idea who it was. So thank you, whoever you were, NASA secret admirer. But good encouragement to stay masked until we've got this COVID thing kicked. Okay, so I'm going to show you guys a program. I've shown it in the past, but I think it's a really nice little program. It's called Stellarium, and it is a sky visualization tool. Hopefully you guys can see this. A sky visualization tool that allows you to see what the sky looks like at any arbitrary time, whether it's tonight or tomorrow night or next year or in 1,000 years, and from any arbitrary location on the surface of the Earth. So you could do it from here or Mexico City or Antarctica or whatever. And it allows you to see what the sky looks like from that place. So this is now, and this is here in Pasadena or Los Angeles, what you would see if we didn't have clouds blocking our views of the sky. And so as you can see, there are a few pretty identifiable things. Most people, one of the more identifiable constellations is Orion here. It's usually identified because it has these 3 bright-ish stars in a row called Orion's belt. And then it has these bright stars. Betelgeuse is quite notable. It's been in the news recently because we think that it might undergo supernova at some point soon, although soon in astronomical terms is like the next 10,000 years. So it could be tomorrow or it could be 10,000 years from now. And a couple of other bright stars. But the cool thing about the Orion constellation is a few things. One, is if you zoom in here, and you can see this from dark sky sites pretty well, there's the belt here. These are meant to be the shoulders. This is the head. These are his knees or ankles. But this is meant to be like a sheath of his sword hanging at his belt. And if you zoom in, clearly you can see one of these stars is not like the other. The middle star, what looks like a star to maybe your naked eye, is actually a bright nebula of gas and young stars that are pumping out so much energy. They're called the trapezium stars because they make a little trapezoidal shape, but they're 4 very bright, young, massive stars, and they're pumping out so much light and radiation that they're illuminating this cloud of gas and dust around them and causing it to kind of fluoresce or glow. And that's what you're actually seeing, both in this image as well as when you look through a telescope or a good pair of binoculars. You can usually make this out. Even from not so great skies, even from here in LA, you can generally, I mean, not to this detail, but you can usually see the Orion Nebula quite well. And it's really spectacular. It's one of my favorite objects in the sky, partially because it's pretty easy to see, but partially because it's just really incredibly beautiful. Another thing that's useful is once you can find Orion in the sky, you can use it kind of as an arrow. So if you kind of follow that line to one side, it roughly takes you through this star called Aldebaran, which is very reddish looking. It basically takes you through that, and you keep going, and you end up at this thing, which looks kind of like to your eye, it might just seem like a little fuzzy blot, but when you zoom in, it's actually what's called Pleiades, which is a star cluster, and it looks something like this. And even, again, in kind of crummy skies where you might have a lot of light pollution, like Los Angeles or New York or other urban areas around the globe, if you zoom in, you can at least see the bright stars, the brightest 6 or 7 stars that make up the core of the cluster. But there are something on the order of like 1,000 stars present in this star cluster. And it's a reasonably young star cluster. Stars tend to get born in groups as opposed to just like a single star. They're more like a brood of stars that are all born simultaneously. And yeah, the Pleiades are one of the more famous ones. It's really cool, and I highly recommend it. And it's pretty easy to find because you just follow that line across the sky from Orion's belt. And of course, there's a couple of other really obvious things in the sky right now. Mars is quite bright. It's a very bright red looking, well, it kind of looks like a star, but maybe it doesn't flicker so much or move around so much. And if you have a sufficient telescope, you can start to see some of the features on Mars, which are pretty cool. But sometimes with low resolving power on your telescope, it might just look kind of like this, like a bright red dot, which is still pretty cool. I mean, Mars is pretty awesome. And then finally, the moon never disappoints. This is a pretty good rendering of it, but you know, I don't know anybody who looks up at the moon through a telescope and isn't just wowed. It's so great. I really dig it. And it's quite bright because it's near full tonight. If again, you have the opportunity to see the heavens. So I'll, as I said, I'm going to try to get a telescope set up here and set up through the computer so I can take you through the process of actually looking through the telescope and seeing what you can actually see with like a high level consumer grade telescope in one of our future events. And yeah, we just have to wait for some clear weather. So hopefully next month we'll get this going. But enough yapping from me. Sarah, would you like to come on here? Great. Hi, Sarah. How's it going?
Hey, Cameron, I'm good. How are you?
Excellent. Excellent. It's been a rough week, but it's nice that we're here at the weekend and we get to top it off with science. This is going to be super cool. All right. So I would like to introduce our speaker for tonight, Sarah Blunt. Sarah is a second-year PhD student at Caltech. She's interested in the orbits and atmospheres of exoplanets, which are planets that orbit other stars, not just our own sun. And she likes running, singing, and playing cello, and hanging out with her pet dog, Fido. I really like that your dog is named Fido. And I didn't know you played the cello. That's awesome. It's like my favorite string instrument. It's so great. Such range.
Yeah, that's what I wanted to be a cellist before I discovered astronomy. So
really?
Cello is my first love.
Oh, when did the transition take place? How old were you?
Like late high school.
Okay.
Right
do you
before.
So you still play, do you play in the Caltech orchestra?
I play in chamber music through Caltech.
Okay, cool. Nice. Well, we'll have to have you back for a performance on one of these events. Okay, awesome. Well, I'll let you take it away. Thank you for joining us tonight.
Thanks, Cameron. All right. Thanks again, Cameron, for the intro. All right, everyone. So tonight I'm going to be giving you an insider's look behind science headlines. As Cameron said, I'm a second-year astronomy PhD student. So I'm studying to get my PhD at Caltech, and I'm interested in exoplanets, or planets orbiting other stars. So I want to start off this talk by just throwing up a plot and not explaining it, and just saying that in 2018 we made this plot and we were really excited about it. We saw this and we went, whoa, that's so cool. And the point of this talk is just going to be to explain to you why we thought it was cool, basically. So the first goal is to explain why I and other exoplanet scientists thought this was cool, why we in particular were so excited about this result. Then I'm going to talk about the process by which this discovery got converted into like science news that you might have seen on your phone or on any of the sort of news apps that you get. And finally, I'm going to share my reflections on this process of going from discovery to science headline and sort of musings about science news in general. And I'm also going to ask for your opinions. I'm really interested what people think. So I've got this handy little outline at the bottom here. The first part of the talk will be all about the science. The second part is going to be all about the story. And then the last part is going to be my thoughts. So those correspond to these 3 bullet points. All right, so let's dive right into the science, part 1. So the main question that I'm going to be trying to answer here is, why were exoplanet scientists excited about this discovery? So there were several reasons that we were excited, but I'm going to focus on 2 main reasons because I only have half an hour to talk to you about this. All right, so some background behind reason number 1. First, I have to tell you what an exoplanet is. So as I've mentioned a couple of times, an exoplanet is just any planet orbiting another star, so not orbiting our sun. So some fun trivia about exoplanets. The first one was discovered in 1995. So this field is about as old as I am, if you're keeping track at home. We've discovered over 3,700 exoplanets. That number is from a couple months ago. It usually goes up by, dozens or so per month, depending on the month. And exoplanet research is also one of the fastest growing fields of astronomy research. People like to make up statistics about like how many astronomers will study exoplanets 20 years from now, but there are a lot of people that are interested in exoplanets and it's still really fast growing. So there's a lot of cool discoveries that you still have to look forward to from this field in the future. All right, so one of the main things that exoplanet scientists have to contend with are that there are many different ways to find an exoplanet. And each method has its strengths and weaknesses. So the way that exoplanet scientists usually explain these strengths and weaknesses is with this kind of diagram. If you ever go to a conference for exoplanet studies, you get so tired of seeing this diagram because you see it at the beginning of literally every single talk you go to. Let me walk you through this a little bit. So on the bottom, this is orbital period in days. So orbital period is just the length of the year of the planet, so the amount of time that it takes the planet to go around the star. So Earth's orbital period, or Earth's year, is 365 days. So that's about here. So you can see that most of the planets that we've discovered are actually shorter orbital periods than Earth. Most of them have very, very, very short years relative to Earth. The other thing that's being plotted on the y-axis here is the mass of the planet. So this is in terms of Jupiter masses. So here's the line of where Jupiter is. So you can see we've discovered a lot of planets that have around the same mass as Jupiter and very few planets that have smaller masses. Earth is like down here, sort of off the scale. So we've discovered very few planets that have the mass of Earth. But you'll notice several interesting things about this diagram. First of all, just that there are planets that have been discovered that are clustered in lots of different areas of this diagram. So for example, this region here, we've discovered lots of planets that have very short years, that go around their stars very, very quickly and have very high masses. So this is called the hot Jupiter class of exoplanets. We've also discovered a lot of cooler Jupiters or warm Jupiters, depending on who you are. And we've discovered this huge population of planets that are bigger than Earth, but not quite as big as Jupiter. So these are called the super Earths or sub-Neptunes. There's also this huge dearth of planets in this sort of region here. And that's because of selection effects. So this basically just means that it's really hard for all of these techniques to get at planets in this region. So it's not that there aren't any planets here, it's just that it's really difficult to find them. So I'm going to focus on one method in particular in this talk. I'm not going to really explain how this works, partially because there was a great talk by Ryan Rubensall on this channel a couple months ago. I don't know what time is, but a while ago. So if you want to dig really deep into how the radial velocity method works, I encourage you to go watch his talk. And also because it's not really necessary, and I only have 30 minutes. So the only thing you need to know is that the radial velocity method, this method that I'm focusing on for detecting exoplanets, is limited by the observing baseline. So that basically means that planets that are farther from their stars are harder to see. So you can see that if you focus on all the blue dots in this diagram, they're all scattered throughout this sort of smaller, shorter year or orbital period region. And as you get out to longer orbital periods, there are very few of them. And that's just because they're very hard to find out here with this particular method. So if you want to get around this observing baseline problem, there are several different ways you can do this. I'm going to focus on two that are relevant for this discovery. So the first thing you can do is just observe for a really long time. So the radial velocity method involves taking a snapshot of a star, measuring its speed, and then coming back later and measuring its speed a little bit later. And so if you take these measurements of how fast the star is moving over a time range that's comparable to the year of the planet you're trying to find, then you see the speed sort of wiggle. And that allows you to infer the properties of the planet that's orbiting it. So the way you can find planets that have longer years is just to look at the star for a longer period of time. So just come back and take these measurements over a very long period of time. So you can do that. And you can also get lucky. And this is related to the shape of the planet's orbit. And I'll talk a little bit more about that in a minute. So to make this discovery, we actually did both. We got lucky and we observed for a really long time. So going back to this mystery diagram that I flashed and didn't explain at the beginning of the talk, I'm going to try and break it down for you a little bit more now. So in terms of observing for a long time, I'm going to call your attention to the top axis here. So this is the year that each observation was made. So what's going on in this diagram is that each one of these measurements is a measurement of the speed of the star. So you can see that each of the different symbols corresponds to a different telescope that was observing the star. So we've been looking at this star with several different instruments since before 2000. So as long as I've been alive, people have been observing this star. Because we observed for more than 20 years, we were able to see that the star's speed suddenly changed very rapidly. And that allowed us to infer that there was a very special and interesting exoplanet there. So the shape of this curve is related to how we got lucky. So the idea here, let me sort of orient you to what you're seeing in this diagram before I play this little animation. So on the top here, I'm showing what the orbit projected on the sky looks like. So you have a star at the center, and then this is the planet. And here's the path of the planet's orbit. So this is actually a circular orbit, even though it looks like an oval. And the reason that it looks like an oval is because it's been tilted slightly relative to your line of sight. So imagine you have a flat pancake orbit, but you're looking at it at a little bit of an angle, and that's why it looks tilted. On the bottom here is a measurement of the star's speed over time in years. So this is 20 years. This is comparable to the time that we've been observing this particular object that I'm talking about. And what I'm going to do in this animation is I'm going to change the eccentricity or the shape of the orbit. And I want you to watch down here what happens to the stellar speed as the orbit changes. So let me play it. So first, everything's staying the same. The planet's just going around its orbit. And then now I'm starting to increase the eccentricity of the orbit. So you can see up here, the orbit gets more oblong. It gets more shaped like an oval. And then you can see down here, the shape of the orbit's very sharp. So it's got a similar feature to this diagram, this very sharp sudden peak, and then this period of very long sort of flat behavior. And then another thing I want you to notice is that when the planet is on the circular orbit, it spends the same amount of time in each part of the orbit. So it goes around at basically the same rate. But when I increase the eccentricity, when I make it more ovally, the planet starts to take a long time in this region, but then when it gets close to the star, it sort of whiplashes around. And that corresponds to this peak. So the reason we got lucky is because we happened to find a planet that was extremely eccentric. It had an orbit that was shaped very much like an oval. And it's lucky because if you can observe during this very sharply peaked part of the orbit, you can learn a lot about the planet without having to wait the entire time. So this planet that we discovered actually has an orbital period, or a year, that's much, much longer than the time that we were observing. So we've only been looking at it for 20 years, but we can infer just based on the shape of this peaky part of the observation that it has an orbital period or a year that's close to like 60 or 75 years. So this is the crux of reason number one that we were excited about this planet. So our combination of luck with getting this funny shaped orbit that had a lot of information in it, and patience, just looking at the same star for 20 years and waiting for it to do something different, this allowed us to actually push the limits of the radial velocity technique. So here's this planet that we discovered, and it's plotted on that same diagram that I showed you before of the length of year of all of the planets all of the exoplanets that have been discovered and their masses. So you can see that this planet sits in a sort of lonely region of this parameter space. It's actually the longest period exoplanet that's been discovered with this particular technique, the radial velocity technique. And whenever I tell that to my mom, she says it's like having the largest carpeted mall in the country. You're not quite it's not the longest planet discovered. It doesn't have the longest orbital period of any planet, but it is the longest in this particular subclass of planets. So it's not the largest mall in the country, it's the largest carpeted mall in the country. So that's reason number one. We could push the limits of the radial velocity technique. So reason number two is that the planet was also exciting because of the shape of its orbit. So the reason that this is exciting is because planets form on circular orbits. So here's an animation that starts with a protoplanetary disk. So this is just dust and gas that surrounds a newly formed star. And as this animation plays back, you'll see this disk transition into planets on circular orbits. So you can see that there's not huge variations in the speeds of the planets, and they go around basically in circles. They don't have any like oval components. The only reason that these don't look like perfect circles is because this disk is tilted relative to your line of sight, just like the orbit that I showed you before. So we start off with this disk, everything forms in nice circular orbits, and then this animation is also showing those planets interacting over time, and so their orbits change slightly. So these tracks actually start getting pulled by one another. So the orbits don't stay perfectly circular. So this planet's orbit that we discovered was really not circular. So the only way that that can happen is if something kicks it, basically, if it has a close gravitational encounter with another object. But the problem was that we couldn't find anything capable of doing the kicking. And just to give you a sense of all the different places we looked for something that could possibly kick this object, here's a little animation. So here's the star that our planet is orbiting around. So the star itself is called HR 5183. Here's the planet that we discovered. It's called very creatively HR 5183b. And then we looked for several other things that could kick the planet. We looked for other planets in the system that could have come really close to that planet and maybe been ejected. We didn't find anything. We also looked for stars that would be very far away, and also stars that were pretty close, stars that were relatively closer using two different techniques that I won't go into too much. So we didn't find any stars like this. we actually did find a star that was very, very far away and could possibly gravitationally influence this planet, but we actually decided that it was too far away. It's actually 12,000 times the distance between the Earth and the sun, 12,000 times farther than the Earth is from the sun, away from this star here. So we determined that even though it's probably moving through the galaxy in the same direction as this planet, it's probably not having a direct gravitational influence on the planet. So importantly, it's not capable, we think, of kicking this object. So the crux of reason number 2 of why we were excited about this planet is that it was a mystery. So we saw this huge eccentricity, this huge weird shape in the planet's orbit, but we couldn't find anything that made it that way. We didn't know how it formed. So that was the crux of why we were excited about it, reason number 2. So just to summarize so far, there are 2 main reasons why we as exoplanet scientists were excited about this planet. The reason number 1 was that it allowed us to push the limits of the radial velocity technique. Its year or orbital period, or how long it takes to go around its star, is the longest of any planet discovered with the radial velocity technique. It's the largest carpeted mall in the country. Reason number 2 is that the shape of its orbit was a mystery. We didn't know how it got that way. So we published a paper about this. We were very excited about it. All right, so part 2, the story. So we had this discovery, we had this paper, we had this figure that I was excited about that I flashed at the beginning. And now I want to tell you a little bit about how this went from a science discovery and something that scientists were excited about to news, or something that we hoped that, that everyone would be excited about. All right, so a little bit about the process of how this works. First, we decided to do a press release. Press release involves writing a sort of pop science summary of the paper and creating like media things that go along with it. So we made a set of pictures and videos and things that could be released to the press. So making this press release involved collaborating with 3 different press offices, which was something that I didn't anticipate ahead of time. So we collaborated with the Caltech press office. We also collaborated with the McDonald Observatory press office and with the Keck Observatory press office. So those were 2 big observatories that had contributed to these observations. And most excitingly for me, we also collaborated with a science artist. So we had someone take my like coded up plot and make it into this really nice movie. So here's the planet itself. This is HR 5183b, and we've got this path of its orbit. And here it is overlaid on top of our solar system. So you can see that all the planets in our solar system are very circular, and then HR 5183b has this wacky egg-shaped orbit. Another thing you'll notice about this planet is that it's really far out compared to all the planets in our solar system. So let me pause it here for a sec. So this is the orbit of Jupiter. This is Saturn. This is Uranus. So HR 5183b, over the course of its orbit, it goes within the asteroid belt of our solar system and then out beyond the outermost gas giant planet. So it's really sort of whiplashing in and out of the solar system. So from there, we released this press release, and then science journalists picked up the story and adapted it. So here's just a sort of sample of some of the articles that people wrote about it. So we've got headlines like, "This exoplanet has the weirdest orbit we've ever seen," and "Astronomers find giant exoplanet with extreme orbit." So you can see that these have already become a lot more like catchy than the way that I sort of have been explaining it to you. So some journalists chose to interview me and my co-authors, while some just adapted the institutional press release. So I recently looked back at my Twitter account to see how I was feeling, to sort of remember how I was feeling about this at the time. And I was in England at the time, and I was actually more excited about like all the Harry Potter tours. So here's a picture of the thing that I actually posted the night that I was interviewed. So this night I was interviewed by BBC and NBC, and I decided to post about platform 9 3/4 instead. But yeah, that's me. So as the story spread around, another thing I wanted to sort of point out is that it got less and less accurate. And the the headlines got weirder and weirder. So here's a sample of like the sort of headlines that happened at the beginning of the story's lifetime and then at the end of the story's lifetime. So the first headline says 3 times the mass of Jupiter, first of its kind planet swings around its star on a bizarre path. So that's definitely very catchy, but I liked this headline because it had actually both of those key science takeaways in it. It had the sort of first of its kind, so the fact that it's pushing this radial velocity technique. It's maybe not exactly the way I would say it, but it's sort of nodding to that extension of the technique itself. And then it says it swings around its star on a bizarre path, so it's mentioning the eccentricity. And then you can see this later headline is Science Line's Guide to the Exoplanets, the Bouncy Ball, HR 5183b, a world caught in a stretched loop. So I had no idea what that was about. Which isn't, also I should make it clear that I'm not necessarily like, I'm not, trying to call out anyone who wrote any of these particular articles. I'm just sort of taking you through the process of how this is a telephone type thing. So we're starting with the press release that me and my collaborators had a lot of sort of input on and control over. And then the story sort of grows beyond where you can control it. So the information gets necessarily diluted across as it keeps swinging around the internet. So the story was in Popular Science News for about a few weeks. This is my 15 minutes of fame, and then it petered off. So personally, this period of my life was really wild, and it was a roller coaster of ups and downs. I liked the challenge of communicating my science to a broad audience. It was sort of invigorating and interesting. The attention that I received was not all positive, especially as a woman scientist, and that was really weird and upsetting to me. So yeah, it was very mixed. Lots of goods, lots of bads. All right, so I've already sort of started transitioning to my thoughts on this. So the reason that I'm, branding this as my thoughts and not necessarily like the thoughts of, I don't want to take credit for how all scientists think about this process. This is also sort of my reflections on the process as a whole. And yeah, at the end, I'm going to ask for your thoughts. And I'd also be interested to hear the thoughts of the other experts on the panel on this as well. All right, so what do I think about this? So thought number one is that I think that what's exciting to the public isn't necessarily what's exciting to astronomers and vice versa. So I wanted to compare for you the two sort of main reasons that I've justified to you are why we as exoplanet scientists were excited about this discovery, and then one of the articles that I thought was actually one of the more accurate articles. So remember, reason number one that we were excited is that it allowed us to push the limits of this technique. So the year of the planet is the longest of any planet discovered with the RV technique. And reason number two is that the shape of the orbit was a mystery. So we didn't know how it got that way. Importantly, it wasn't that we had never seen an orbit with a planet with that orbit shape before. It was just that we didn't know how it got that way. We couldn't explain the orbit shape. So when you sort of break down this headline of this exoplanet has the weirdest orbit we've ever seen, it's not necessarily true. We've seen actually much more eccentric planets. So if you want to quantify it, this exoplanet has an orbit with an eccentricity of 0.84, from a 0 being perfectly circular and 1 being like completely unbound, like the most possible elliptical orbit. So we've seen planets with eccentricities of like much greater than 0.9, like even like 0.99. So 0.84 was high, but it wasn't crazy. It was more that the shape of the orbit was a mystery. So this discrepancy can lead to misunderstandings. So there were I broke these down into two classes of misunderstandings. The first is sort of the really out there misunderstandings that I think would happen with any sort of, anytime you talk about space, you're always gonna have people thinking about aliens and spaceships. So we got a lot of these types of comments of, it's not a planet, it's a spaceship. And this is just on the YouTube, so I didn't feel too bad calling out this person by name. I hope they're not watching. And if they are, I hope that they don't feel bad. There were a lot of people that had this thought. And then the second class of misunderstandings I thought was very interesting because I think it reflected more on our ability to communicate the science than on, the people, someone's ability to understand it. So I got this, I couldn't find this comment. I couldn't remember who made it where, but I thought this was a really good and interesting comment. So someone said, congratulations, you've discovered Mars. And that might not make sense if you first look at it, but when you think about it, Mars has some eccentricity. So every planet in our solar system has a non-zero eccentricity. Granted, they're very small compared to the eccentricity of HR 5183b, but they're still there. And in a broader context, we've discovered other planets with eccentricities before. So this comment was pretty well motivated. They were picking up on the fact that we were focusing on the exoplanet's eccentricity and not necessarily the mystery that was behind the eccentricity. So I thought that was interesting. All right, so I've focused a lot on the negatives, so I wanted to end with a positive. I think the net effect of this process is positive. So here were some positive things that I thought came out of this. So first was that I got a lot of emails from young people who were interested in astronomy, which was just fantastic. I really loved talking to high schoolers and college students who are interested in getting involved in astronomy. And it meant so much to me to see people like reading about this discovery and getting interested in astronomy because of it. The second sort of net positive is that a lot of people did understand the mystery and sort of zeroed in on the same questions that we were interested in. So I like this comment in particular. This person says, what's causing this? Why aren't the other planets behaving in a similar manner? And that's literally like the focus of the paper that we wrote. Like that's what we're trying to answer. That was what we were trying to figure out. So I thought that was cool. And that was great that people actually got sort of the main point that we were trying to communicate. And the third sort of net positive, which I don't have more like specific examples of, is just that I think public interest in exoplanet studies in general is bolstered by interesting discoveries like this, which I, as an exoplanet scientist, like. I want people to be interested in exoplanets. And I also I want to be doing something that people care about. I don't want to just be doing my science in a vacuum, having no one ever read my papers or my thesis. I would like to, contribute to the net human understanding of the universe. And I think that involves everyone. I think that has to mean that everyone understands. It doesn't matter if I'm the only one that understands this particular part of the universe. All right, so that's all I had to say. At this point, I'm really interested to hear your thoughts. I've expressed a lot of opinions in this talk. The first half was sort of laying out the facts of the discovery, and then I just sort of, talked a lot about what I thought. So I'd be interested to hear in the YouTube chat. Feel free to comment without necessarily asking a question. So I would love to know why you think scientific press is valuable and whether or not you feel that scientists do a good job communicating why certain discoveries are important. And then of course, me and the other 3 experts are going to be hanging out for the next hour and 15 minutes or so to answer any questions you have about the science of this talk, about science communication, about scientific press, or anything in the universe. All right, thanks.
Great presentation. Thank you, Sarah. Very illuminating the whole process of going to the broader press. I've seen peaks of it, but I've never been involved in that process. So it's nice to see it a firsthand account. Thank you. Tony and Amruta, can you both join us again? Excellent. Okay. So we encourage everyone in the audience to write their questions and comments in the chat, and we will try and address the questions, all 4 of us. So obviously you're familiar with Sarah and the science that Sarah works on, since she just gave our this wonderful presentation to us all. I'm Dr. Cameron Hummels. I do computational astrophysics, focusing on modeling the evolution and formation of galaxies and galactic systems and the gas that surrounds those galaxies, and how just kind of the broader structure of the universe and what that means for us. So I'm happy to answer questions on that. Amruta Jaodand is a postdoc at Caltech. And do you want to introduce like what you work on? Except you're muted.
Oh my God. After a whole pandemic, one would think I would know how to use Zoom. So, yeah, hi. My name is Amruta. I'm a postdoctoral researcher at Caltech. The things that I work on is, these stars called neutron stars, which are left as remnants of when a star dies and it undergoes a supernova. You have this massive dense star that's left behind. And what I'm particularly interested in is when these neutron stars have companions and they undergo violent outbursts using, a variety of telescopes and chasing these intense outbursts to try and catch. I'm sorry, guys. That's just my dog. She wants a lot of attention because it's Friday.
Okay, we all need attention.
Yeah. So that's what I do. And I use specifically the New Star telescope, which is at Caltech, which is a high energy X-ray telescope. And I would be happy to talk about, X-ray observations of neutron stars, how some of these neutron stars are lighthouses in the sky, etc.
Okay, great. If you want to allow the dog into the frame, I'm sure our viewers would appreciate the opportunity to see your fine canine. Tony Rodríguez is a PhD candidate at Caltech in the Astronomy Department. You want to talk about what you're working on as well?
Hi, yeah, of course, Cameron. Thank you. Yeah, my name is Tony. I'm a first-year grad student here at Caltech, pursuing my PhD in astrophysics. And the problem I'd say that I've worked the most on has been star formation, in particular, really weird events, really weird outbursts that happen in young stars. I'm venturing into other projects right now, something related to something called gravitational microlensing, and that exploits Einstein's theory of general relativity to try to probe things that would be very difficult to study otherwise. And yeah, feel free to ask me questions related to any of those topics or astronomy in general.
Awesome. Okay, great. All right, let's launch into the questions from our audience. Let's see. And I encourage our speakers to check out, or our panelists to check out the Google Doc where I'm writing some of the questions as well. Let's see. Sarah, I think this one is for you based on the talk. How do we know that the planet that you've seen is in an orbit and not a rogue planet on a flyby?
That's a great question. So actually, we could identify rogue planets by their eccentricities, the same parameter that we use to sort of solidify this planet as a mystery. So eccentricity goes, I said it goes from 0 to 1, but that was actually a simplification. You can have an eccentricity that's greater than 1 as well. And that basically just corresponds to a flyby. That means that the planet is not bound. It's just interacting gravitationally with the star sort of once, and then it goes back out to very far distances away. So we would actually see something like that in the shape of the star's speed versus time curve. So the fact that the shape did not look like we would expect for a rogue planet means that this planet is bound. That's a great question.
Okay. So just a personal question I had about your discovery. So you said the eccentricity of the system, it was pretty eccentric. You said it was like 0.84, 0.7?
Yep. Yeah, 0.84. Mm-hmm.
0.84. But then you said that there were some exoplanet systems that we saw eccentricities of like 0.99. So it's like, whoa, like really, really almost like a radial orbit where it comes all the way in. Are those, how come they don't have super long periods? It's just really close to the host star? Yep,
yeah, that's exactly the reason. So there's a sort of sweet spot where we've seen more eccentric planets. Actually, don't quote me on the 0.99. I don't know that that's the most eccentric. We've definitely discovered more eccentric planets than mine, but maybe it's like 0.95 or something. But yeah, they all have shorter orbital periods. They can't be too short, actually, because if you get close enough to the star, the orbit circularizes very quickly. So basically, all of the angular momentum in this orbit just goes away. It transfers to the star. And so the orbit shrinks into a circular orbit. But there's a sweet spot in between those very, very close orbits that are necessarily circular and this very, very long period, decades long orbit that we discovered of several days to a couple of year long orbital periods that are more eccentric but take shorter times because they're closer.
Okay. One of the first questions that we had, what is the proper motion of the host star and how does it compare with others in our in the local area?
Yeah, it's another really good question. So we were actually pretty interested in this question for a while too. So for those that don't know, the proper motion of the star just refers to one measure of how the star is moving through the galaxy, basically. So how this star compares to other surrounding stars. So this star is classified as a high proper motion star, which just means that it's moving. If you look at it on the sky, it moves a lot over periods of decades relative to other stars. And the reason for that is just because it's pretty close to us. So there's nothing special about it. It's just a lot closer than other stars. So because there's because it has some difference in the way it's moving through the galaxy relative to us, we see it moving faster. For a while, we thought that this star was a galactic halo star. So we thought that this was in a special part of the galaxy. And we thought that there was possibly a chance that the galactic halo stars tend to have more active lifetimes, more interactions than other stars. And so we thought that maybe that would explain why the planet got so eccentric, but some dynamicists, some galactic theorists told me that that was not true. And it turned out not to be a galactic halo star after all. So it's pretty run of the mill. It's got a standard proper motion that we would expect for that star relative to others in its vicinity.
Okay. Oh yeah, just as a quick response, because Chris asked about eccentricity values. The question is E greater than 1 hyperbolic? Yes. So E of 0 is a circular orbit. And correct me where I go wrong here, guys, but E of 0 is circular. E of between 0 and 1 is elliptical. And then once you get to E equals 1, then it's a parabolic, where it's unbound at one end, and then E greater than 1 is hyperbolic. So it just goes flying away. It's not bound. It's not gravitationally bound to the system. So for instance, the comet or the interstellar asteroid, Oumuamua, I'm probably screwed up the pronunciation of that because I do that all the time. That was on a hyperbolic orbit. It's not bound to our system. It came in from interstellar space and then got flung out. And you probably have seen it in the news in the last week because Avi Loeb, who is the chair of the Harvard Astronomy Department, just wrote a book trying to sell a book saying that it's aliens. Nobody thinks it's aliens. None of us astronomers thinks it's aliens. Do you guys think it's aliens? I don't think it's aliens. I think Avi is taking a very controversial position by claiming that it's aliens, and I think it's too bad that someone in that position is making those claims, because there's a lot of other potentially natural explanations for that weird object coming in, and it does have weird properties, but don't invoke aliens as your first. I'll get off my soapbox here. Sorry guys. Anyway, let's deal with some more questions. Is it possible? Well, here, let me jump to a different question, so it's not just all Sarah and me. I'm just yapping too. Does Gaia data impact your research? All of our research. And I've heard that we can find exoplanets from Gaia data. So who wants to chime in? Obviously, Sarah can chime in. I think Tony can probably chime in.
Yeah, I'm happy to answer the first part of this question. For the general audience who doesn't know what Gaia is, Gaia is a satellite launched in space by the Europeans, the European Space Agency. I think they sent it up a while ago. And all it does is something very simple. It has a telescope on it. And it does something very simple. It just measures the distance to stars, to objects in space. And you would think that, astronomers are smart. Surely they can figure out distances to things. It's very difficult. And knowing precise distances to things in space is actually a huge, huge challenge. And some of the most important frontiers in probing the farthest depths of the universe. So Gaia doesn't probe the farthest depths of the universe. Gaia probes the very, very, very local universe. But the point is that if you want to explore the really, really deep universe, the distances keep getting harder and harder and harder to measure. But distance is very crucial. So Gaia's doing great science in just being able to give us more precise distance measurements. And some really quick sort of toy project that I worked on in these past few weeks was using the newest Gaia data release. So Gaia releases its data every couple of years, I'm not sure how often it actually is. But with the newest data release, it released an updated distance measurement for this particular system of a giant star with a black hole, what's believed to be a black hole companion. And a super big mystery is what is the boundary between black holes and something called a neutron star. It's a very, very dense type of stellar object. And what this new Gaia measurement to the distance of the system provided was it said that the mass of this black hole was even lower than we had expected. So it corrects our data, corrects our understanding in a way that for planets, I imagine, is also very, very important. But in this other subfield of astronomy, at least, it could be pretty important. And that's just like a really simple, quick example of something that the Gaia is able to provide us with.
Excellent. Sarah, do you have anything to add on how Gaia impacts your science?
Yeah, so Gaia is going to find a lot of exoplanets, we think. So currently we've done 3 Gaia data releases. And so far, Gaia hasn't released time-resolved astronomy. So astrometry, sorry. So that just means that we're only getting average measurements of position and speed for stars rather than the distance over time of the star. And in order to find exoplanets, we need that sort of distance over time. We need to look for something that's wiggling back and forth because a planet's tugging on it. So once that data release happens, which will probably be in a couple of years, it will be at some point. It's not probably someone, I just don't know exactly what the date is. But then they'll find a lot of exoplanets. Aside from that, Gaia has already been really useful for exoplanet science because we can compare this average motion to the average motion measured by a precursor satellite that did something similar called Hipparcos. So you can look for differences in the speed of the star in one direction at one point and then 20 years later in another direction. And so that generally isn't enough information to discover new planets, but it can put constraints on the orbits of planets that we already are aware of. So planets that have been discovered with other methods.
It seems like the sheer number of stars that are being observed by Gaia, when they do release this time domain information that shows the wiggle of the astronomical information, the position on the sky of all these stars, couldn't that be, like you were saying, that the number of discovered exoplanets every month goes up by a couple of dozen from, this study over here, or this group over there, puts out a couple of papers and this group puts out a couple of papers. But wouldn't the Gaia data release just be such a huge amount of information and stars that it would jump from 4,000 discovered exoplanets to 20,000 over the course of a couple of months, wouldn't it? I don't know. I don't work on exoplanets, but it just seems like it would be very easy to do analysis on all those positions and get out the masses and velocities of these various different planets. So I don't know. Do you think that that'll happen?
Yeah, absolutely. So the really exciting answer to your question is that Gaia is not the only mission that's going to happen for. So there are many upcoming missions that are going to do this huge data dump and, tell us about thousands of planets all at once. TESS is already doing that. Kepler did that. We discovered thousands. Most of the discovered exoplanets were from Kepler. And TESS just hit 100 discovered planets, and it's increasing rapidly, the number that TESS has discovered. And yeah, overall, the number of exoplanets discovered is exponential growth as a function of time, and it's going to continue to do that.
That's pretty exciting.
Yeah, so specific yield estimates for Gaia are varied. Like some of them there are different estimates based on different assumptions. Like one thing you have to assume is the underlying eccentricity distribution of planets. We don't necessarily have good constraints for longer period planets, what the eccentricity distribution is. We're getting better, but it's not perfect. And so that might, since there's different amount of information in eccentric orbits versus circular orbits, that'll change the number of planets we can discover, et cetera, et cetera. There's lots of different assumptions that you can go into. So some people say it'll be like, tens of thousands of exoplanets discovered, and some people will say it'll be a few thousand, but it'll be a lot. Gaia's going to be great.
That's cool. That's very cool. Okay, so we should stay tuned over the next couple of years for like a lot more discovered exoplanets, is what you're saying.
Definitely.
Okay, I dig that. Amruta, do you have any ways in which Gaia has influenced your research?
Yeah, actually. So one of the things that we deal with a lot in pulsar astronomy is that, most of the pulsars are like, neutron stars are isolated, considered to be by themselves. But because of Gaia's new measurements of, the astrometric measurements, now we're beginning to see that, many more of them have companions. For example, 8 young pulsars had companions that we did not know of before. And Gaia was able to tell us about it. What it also does a great job of is putting kind of an upper number or upper limit on what is the neutron star merger rate using the Gaia sample, which is very crucial when you're looking at the future of our gravitational wave astronomy, and you're looking at different types of neutron star populations. So in that way, Gaia has really helped us. And I've been using the distances Gaia put forth for some of the old pulsars because they don't get monitored sometimes because they just get boring and they're so stable and who wants to look at them? So Gaia does a great job of that. So yeah.
Great. Yeah. Yeah. Gaia, I think, has been a huge boon for a lot of different subdisciplines within astronomy. As somebody who does galaxy evolution, I mostly worry about the distribution of gas in the galaxy, but certainly the dynamics and the distribution of the stars has been revolutionized or certainly the study of our own galaxy, the Milky Way, because that's the stars that it's picking up, has been revolutionized by the data releases from Gaia. So it's been a very successful project. Okay, let's see. More questions from our audience. Here's a different one. Do neutron stars really get smaller as they gain mass? Who would like to take this one? You can talk about degeneracy pressures and such. Because it is weird, right? You think, oh, I've got this thing. Here, I've got a nice little exercise. Well, I've got this nice little neutron star. And as I pack more and more stuff onto it, you would perhaps intuitively think that this would grow. It would get bigger. But in the case of a neutron star or a white dwarf, it actually, as you pack more and more stuff onto it, it shrinks in size. I can talk about it all day, but do other people want to talk about it? Okay, I'll talk about it all day. Okay, so neutron stars and white dwarfs are kind of funky in that they are composed of, like white dwarfs, in the case of white dwarfs, they're mostly composed of electrons. And in the case of neutron stars, they're, as the name suggests, mostly composed of neutrons. And both of those subatomic particles have to behave according to quantum effects. In this case, the Pauli exclusion principle that says that you can't have two particles that are in the exact same place and have the same like quantum quantities. And so what that essentially means is you can only squeeze them so tightly together. And so so that's the pressure that's holding it up. Anytime you have a gravitationally bound object like a star, it's defined by two different forces. It's gravitational force. Gravity is an attractive force. So if I have got to find things to use for my example. If I have my phone, which has mass, and if I have this neutron star, which has mass, because they both have mass, they are pulled towards each other. Gravity pulls them towards each other because gravity is an attractive force, just like it's pulling you towards the Earth because you have mass and the Earth has mass. But in the interior of a star, gravity's holding it together. But at the same time, if there weren't anything opposing that force, it would just collapse into nothing, into a singular point, which is what a black hole is. Let's not get into black holes for the moment. But in the case of a star, a normal star like our sun, you eventually, as it collapses, it gets so dense in the core that you ignite nuclear fusion, and then as you're cramming nuclei together, they release energy, and that energy pushes up. It creates essentially like a hot gas that's opposing the collapse of the gravity, and then you get something called hydrostatic equilibrium, which is just a way of saying everything is static. Everything's stuck because the gravity's pulling in and the pressure from the nuclear fusion is pushing out. You don't have nuclear fusion in a neutron star. The thing that's pushing out is this quantum effect, this neutron degeneracy pressure, which is essentially preventing the neutrons from all going down to a single point in space. But it turns out neutrons can really press together really, really close before that pressure takes over. And that's why neutron stars are so dense. You may have heard these statistics, like you can take a sugar cube of neutron star material, and if you were to weigh it on a scale, it would weigh like the same mass as New York City. I don't remember the exact value, but it's a lot. It doesn't weigh like a sugar cube's mass amount. It's more like the mass of a city or a mountain, because it's so dense. And so what happens though is when you add more and more mass onto a neutron star, you're increasing its mass. So you're increasing its gravitational pull and the amount that it can pull itself together and collapse. And so it shrinks. It shrinks because it has more mass, it has more gravitational attraction, the potential's lower, so it squeezes down even tighter and tighter. And you can keep doing that until you reach a certain stage where finally you basically upset quantum mechanics, where the amount of motion that has to take place in those neutrons to keep them from falling down to this singularity, to a black hole, is too much. It exceeds the speed of light, and then it collapses and it turns into a black hole, and game over. Then we don't know what the heck is going on. So I guess that was a long-winded explanation of what the heck's going on with neutron stars, but they're really interesting. We don't really understand what's going on in their interior because it's so dense. There's a lot of magnetic fields. It's crazy science, and I mean, not crazy in a bad way, but just like super exciting. And there's a lot of unknowns that we don't yet understand. So it's a really active field of research. And I don't really work on it, but there are definitely people in the department who do. And I guess Ilaria Caiazzo sometimes is a guest on this panel. She works on neutron stars. There's a number of people in the field that are in our department who work on it. So good question. Hopefully I made some sense with all that nonsense. Let's see. Other questions? High metallicity stars, are they a better choice for Jupiter-like exoplanets or high mass Earth-like planets? What do you guys think? Who wants to handle this one?
I literally learned this in a class the other day.
Perfect.
Yeah. Not necessarily the reasons why. I feel like the reasons why aren't super well understood, but the demographics are at least there. The population studies are at least there. Metallicity, just for astronomers, a metal is anything that's heavier than helium. So, periodic table, the elements, we got hydrogen, we got helium, and lithium, beryllium. Some people memorize a whole song for that. I know I had to, like in high school for some chemistry stuff. But that stuff that's heavier, that we call that metals. And you can measure the relative amounts of these higher metals to hydrogen, for example, and say, call that the metallicity of some star. And there's, I guess, this weird relation between higher metallicity stars and higher metallicity systems tend to have hot Jupiters, like one type of planet, on more eccentric orbits. So that's exactly what Sarah's talk was about, eccentricity. So it's like the shape of these orbits. So for some reason, this metallicity, like the presence of these heavier elements, influences the shape of the orbits. I hopefully someone else in the panel is able to, explain why, but that's certainly a demographic that's seen. And I don't think that's the case for terrestrial or more rocky type planets. I don't think that same relationship has been observed. That's as far as I know, but it's certainly very cool. I briefly spoke to a dynamicist about this, and they said something about you can just get more small thing, like more, you have more things that can coalesce, things that can form in these systems, and then they can disturb orbits and they can make them more elongated. I guess that's one explanation. I don't know. I'll leave it to someone else to chime in with this. That's a great question. It's kind of weird.
Yeah, another thing I can add, Tony, I think people don't know why. One potential theory is that stars with higher metallicity form more planets, so they perturb each other, and so they get on these eccentric orbits. But I don't think people know why. Yeah, metallicity, correlations of what types of planets form around which stars with which metal content, it's actually a really active area of research. People are really interested in looking for other correlations and trying to explain why they happen. Yeah, so far the only really well-established trend that I'm aware of is this hot Jupiter metallicity trend. We haven't seen unambiguously trends with metallicity with other types of planets.
Okay. Sorry, I'm trying to figure out what questions to ask next based on the audience's questions. How about, is it possible that another planet was kicked out of the system that you were showing earlier and previously influenced its eccentricity through the Light-off-Kozai mechanism?
Yeah, I really like this question. Where to start? So we thought about, there's actually a paper that's going to be coming out that digs into some of the dynamics of this particular system soon. So I can talk a little bit about the different scenarios that we investigated in this paper. And it's a little bit different. It's a little next step from the story I presented in the PowerPoint. So the two potential scenarios that have a reasonable chance of exciting this high eccentricity are there's a very wide, remember I told you there was a binary star. There's a really, really widely separated star that I told you in the PowerPoint was too far away to have an influence on the planet. So this new paper checked me on that and saw that was really true. And they found that it was not, that it's very unlikely that that binary star could excite the planet's eccentricity. And that would be through the Kozai leadoff mechanism. So this mechanism involves secular angular momentum exchange. So that basically means the eccentricity and inclination, so the tilt of the orbit of the inner planet exchanges over time due to the outer companion. So it's not really important that you understand why that's happening, but you can imagine just the planet going from being eccentric and tilted and flat relative to the plane of the system, and then more circular and more inclined, and it sort of oscillates between those two different modes. And so that might be one reason why we see this high eccentricity, is that we just see it in one of these modes where it's eccentric and flat relative to the plane of the solar system. So that's the Kozai leadoff effect. we found that this star, as I assumed in my original paper, is too far away for that to be effective. We would only see the star, the planet, in a high eccentricity state a very small portion of the time. The other thing that we investigated was planet-planet interactions. So this is like, imagine, this is sort of going back on the point of what I was telling Tony, what I was not telling Tony, what I was building off of Tony's point before, which is that if you imagine that the system originally had like 2 or more giant planets, and they came close to one another, they could have had a gravitational interaction that kicked one of them completely out of the system and left the one that's remaining with this high eccentricity. So we also found that that is alone is unlikely to have a really high success rate with just 2 planets. But we actually found that if you combine these 2 techniques, if you combine these 2 physical mechanisms, if you have the Kozai-Litoff mechanism from the very wide binary that's causing these eccentricity and orbital plane tilt modulations, and the planet-planet interactions, that you can get this eccentricity a reasonable fraction of the time. So it's not definitely the answer, but it's a possibility. So
Cool.
that didn't really answer your question, but you said Kozai-Litoff and you said eccentricity, so I was like, this is my chance. I'm going to talk about this new paper.
Let's see. Here's a different topic. Are we still sure that supernova type 1As are in fact standardized standard candles? So I guess this comes with a bunch of different things that we need to define, like what's a type 1A supernova, what's a standardized candle, what are standard candle, what are all these things? Who wants to tackle it?
I can try.
Okay.
Okay. So, okay. So first of all, let's start, as Cameron said, what is a type 1A supernova, right? So are you guys able to hear me, or is it a bit? Yeah, okay, cool. So what's a type 1A supernova? So the standard picture about type 1A supernova is that if you have like a white dwarf and it blows up, it gets completely torched or shredded to pieces, there is a really bright explosion. Sometimes it's so bright that it outshines everything that is in sky, even all the galaxies. Now, the thing is, the idea is that, okay, if we have this standard idea of what's, a mass of a white dwarf, we are going to be able to say every time a white dwarf explodes, this is the amount of energy that should be released, right? And so the further these explosions are from us, the lesser luminosity you would observe for a type 1A supernova. So this way you can compare, construct a pathway of mile markers in space by using type 1A supernovas. But here is the thing, as standard as we like to think that they are, theoretically, observationally, the picture is getting much more complicated as we find more and more of them. For example, with the Zwicky, transient facility, which is, an observational facility in optical domain at Caltech, is beginning to find a lot of different types of supernovae, and supernova 1A is one of them. So finding more of these objects is one way that we're beginning to understand that we always give this an idea of, okay, white dwarf is at the standard mass and there's the standard, particular limit called as the Chandrasekhar limit, and a white dwarf cannot exceed that. But we're beginning to find exotic weirdos that, exceed this Chandrasekhar limit. So then the assumption that we had initially that this is the amount of energy that should be released is itself, being questioned right now. The other thing is that till now, we didn't really know. Till now, as in earlier in this decade, around 2015 or so, we didn't really have an observational direct evidence that whatever this thing that was exploding that we call supernova 1A and assumed that was a white dwarf was actually a white dwarf. And so that discovery has only come about in the last decade. And so that's why, I think, okay, these are standardizable candles. So you can still say, for example, I'm not from US. So for me, mile is not a standard unit yet. So, it's kind of like I have to convert in my brain every time there's a mile, and there are so many miles. And so you can still use it as a ballpark figure, but you don't really get the exact sensation of how much the distance is. So there's they're still usable. We can still, use them as the cosmic mile markers, but just with a little bit of pinch of caution that, there are things that we still don't know about them. So, yeah.
Good explanation. Yeah. The standard candles and the distance ladder are always a challenge because every rung of the ladder is dependent on all the other rungs. And so any uncertainties build up. But no, that was a great explanation, Amruta. Okay. There was a question asking, for orbits with near approaches, how much impact does gravitational frame drag impact the shape and evolution of the orbit? So I think what this is asking is, gravitational frame dragging occurs in really, it's a relativistic effect, which is to say it only occurs in really massive environments or traveling at very, very high speeds, or both, which is what Einstein's relativity is generally all about. And I don't think, and you guys can correct me if I misstate this, but I don't think that that when planets are orbiting around stars, that we have any examples of planets that are in the relativistic limit, that are traveling around an object that's just so massive that you start having to worry about relativistic effects. For the most part, we don't have to, like Newtonian gravity works pretty well for defining orbits. Obviously, there's the example of Mercury, like one of the first confirmations of relativity was that Mercury is in a slightly different location than it would appear to be on the backside of the sun during an eclipse, because of the relativistic effects of gravitational lensing from the sun in the way. But that's more the path that the light travels, as opposed to frame dragging of the motion of the planet in its orbit. Frame dragging like that tends to occur for, as I said, really massive objects. So like when a star gets really close to a supermassive black hole, or when two black holes are starting to merge, like the things that are being detected by LIGO in terms of their gravitational waves, then you'd start to see those effects. But I don't believe that it should influence any of the orbits that are associated with planets, because I think they're just too low mass. But if you guys have more info on this, I'm happy to expose my ignorance and be wrong here.
I computed a case of a planet once where there's frame dragging.
Oh, really? Okay.
Yes, this is one of the planets in Interstellar, the one where you've got the tides.
It's orbiting around the massive black hole.
And one of the biggest complaints about the movie, about some people were like, oh no, but that planet's too close to the black hole. There's a special type of black hole, and we talked about this in my general relativity class in undergrad, called a Kerr black hole. It's a spinning black hole. And if you get it to spin fast enough, you can get the planet to be close enough so that it was able to be that close to the black hole. And we like computed it. We're like, okay, it's got to be this close. That's about how far it seems in the movie. And those spinning black holes can have frame dragging, but that's not a real planet. It might be, but I don't think so.
Right. And that was clearly an example. I know. Okay. So for audience members, hopefully you've seen Interstellar. I think it's a really good movie. There's some weirdness to it, but it was originally written by Kip Thorne, who won the Nobel Prize in physics a few years ago and is a professor in the department. So he knows his physics pretty well. And I remember he tells this story that the only way that he would agree to have the film made by Christopher Nolan is there were no modifications to the script that would make something that's physically impossible occur in the film. And so, yeah, the time dilation effects that you see in the film Interstellar, where time, passes at a different rate for the people who are on the surface of this planet versus the ones who are up in orbit away from the planet, because the planet's really close to the black hole, you get these effects. And it is like a crazy orbit and a crazy around this black hole, but it is physically possible. It's just not a very common occurrence, presumably. And I don't think we've discovered any exoplanets orbiting black holes, right? We just know the neutron star one, right?
Yeah, just pulsar planets.
Yeah, just pulsar. Yeah. So, okay. Okay. Anything else to add on that, guys? All right. How about this one? Is it possible to identify a binary system having a star and a brown dwarf? Or a star? I mean, we know of stars and planets, and we know of stars and stars, but what about stars and brown dwarfs? First of all, what's a brown dwarf? Who wants to talk about this one?
I can take this one.
Okay.
So a brown dwarfs are sometimes called failed stars. The exact boundaries are a little bit fuzzy, but of what's a planet versus what's a brown dwarf, and then what's a brown dwarf versus what's a star, but they're intermediate mass objects between the masses of planets and the masses of stars. So we don't have a brown dwarf in our solar system, so we think of them as super exotic, but they're actually very common in the galaxy. So brown dwarfs, you can think of much larger than Jupiter. So the reason that they're called failed stars is that they never underwent hydrogen fusion in their core. So the definition of a star, some people define stars as things that fuse hydrogen in their core, and they shine because they're releasing that energy. So brown dwarfs, by some definitions, don't fuse hydrogen. Being very cagey about what is actually the definition of a brown dwarf, because I've worked on alternate ways to define brown dwarfs. So I have a vested interest in people not necessarily defining brown dwarfs this way, but that is the way that people usually define them. Okay, so the question is, have we found systems with brown dwarfs orbiting stars? And the answer is yes, we've found many. We've also found brown dwarfs orbiting each other, binary brown dwarfs. We've also found brown dwarfs orbiting binary stars, so two stars and then a wide brown dwarf separated. We found binary brown dwarfs orbiting single stars. So there's a whole zoo of brown dwarf architectures that we found.
And related to that, there was kind of a related question. Do we find exoplanet specimens in double stars, binaries, brown dwarf systems, or even double pulsars?
Yeah, I think all of the above except double pulsars. I don't know of planets that have been discovered around double pulsars. Is that true?
Yeah, no, only pulsar planets.
Okay.
Of them.
Yeah, I don't know. Do we? I mean, there's the pulsar planet, the first one that was detected. Is that the only pulsar planet that we have discovered?
There are more now. Apart from the initial one. So the first exoplanet was discovered around, a neutron star, the pulsar planet. But over the years, there are more, not a lot though, I think at most 4 systems which have been found in such a manner. But I don't know of anywhere there is a double neutron star with pulsars going around it, because first of all, finding double neutron star is itself extremely difficult. We have about 3,000 pulsars right now, out of which there are at most 2 to 4 of them are double pulsars, depending on published, non-published results, etc. And so if you take that probability into account, it's taken about 60 years to find 3,000 and find 2. So these systems, must be rare, just by the probabilistic. And then if there is, it would be a rare situation, I think. I don't know of a formation channel by which you'll be able to sustain a planetary system with, 2 different episodes of 2 different episodes of supernova. How would that happen? I don't know how that works.
There. All right.
Can I make a random comment about dynamic stability? Totally unrelated. Amruta, maybe you can work on this for me, because this has been a pet thing that I've wanted to do forever, which is that so I had this crazy idea that the Game of Thrones planet. So, okay, for those of you that don't read Game of Thrones, don't partake, there's this wacky thing that happens that the lengths of the seasons vary dramatically. So they'll have like one time they'll have like 7 years of winter, and then they'll have like 4 years of summer, and then they'll have like 18 years of winter, and like it just goes back and forth all the time. And so scientists have like thought about like, you know, what could be happening? Like there's all sorts of different theories. So my theory is that the planet is on a chaotic orbit. So basically this only happens if you have more than one body in the system. So you could have another star, you could have another planet, or even multiple other planets and stars. And so depending on like the particular path that the planet takes, it sort of gets whipped around into weird different configurations. And so that's why the seasons are changing so much. And so my theory, so this all connects to like how Game of Thrones is actually going to end. And so the theory is that it's eventually going to get ejected from the system, and it'll just be winter forever. And so I posted this on a meme page, and someone actually wrote like a joke paper about this, but I want someone to write like a real paper about this. I want like a serious paper, like this is the theory, like not mention Game of Thrones, just like.
Yeah, and I mean, especially if the planet is light enough, so you know you have like dynamical interactions, and then you capture heavier and heavier planets together and form a system, and it's like yeet out this Game of Thrones planet who, you know, that would be a very George R.R. Martin ending, which is like not just that one person dies, the whole planet like, you know, pops off away from a star, so everybody dies, you know. Yeah, that would be fun.
George R.R. Martin and tell him to write it that way.
Oh no, he'll hold up the rest of the series. It's already taken so darn long for him to finish. He doesn't need additional modeling of the dynamics of the orbit of this planet to mess him up. I posted into the chat. There's a paper. I think there are maybe a couple of papers, but somebody wrote a scientific paper on the potential orbital dynamics that could explain this crazy Game of Thrones. I don't know if that's the exact paper that you were talking about. You said yours was, is this the same paper?
This is the one, yeah. So Adib wrote this after he saw my comment on his meme channel.
Oh, that's awesome. That is awesome.
Wow.
Yeah, that's pretty dark though. It just flies off.
My favorite part of this paper, oh, sorry.
Oh no, I have nothing to say really.
Oh, look at the appendices of this paper. There are some excellent appendices.
Oh, are you mentioned? Yeah.
Oh no, I don't think so. But they have.
Oh my God! Oh my goodness! They did Hodor equals to Hodor equals to Hodor Hodor Hodor. Oh my God!
Yeah. So just for our audience, every April Fool's Day, because it's April Fool's Day and people play pranks, you basically, in the same way that you can't really trust the news that you read that day because people throw in kind of crazy headlines here and there and you aren't supposed to take it seriously, there are always joke papers that are put onto the archive, which is kind of the scientific newspaper where new results come out and new publications hit. And I'm actually kind of surprised that this paper came out on March 28th. They didn't wait the 4 days for April Fool's Day to put out this joke paper. But usually you look on the archive or whatnot on April Fool's Day and you'll see all sorts of kind of joke results or things that oftentimes, again, like the normal news, you read it first and you're like, oh, holy cow, and then you're like, oh, right, it's April Fool's Day. But
yeah. Anyhow.
All right.
Just like these, I realize we actually, are a bunch of nerds. So it's fun. It's fun.
It is fun. How do we confirm the existence of exosatellites for exoplanets, like exomoons for exoplanets? Do we have examples of these?
I can take this one.
Okay.
So we have candidates for sure. Depending on who you talk to in the community, people are more or less completely convinced by these candidates. There are a couple of different ways that people have thought of to try and detect exomoons. So we'll talk about maybe one or two. So one is just looking at photometric variations. So this idea is that this plays off of the transit method, which is one of the most prolific ways that has been used to date to discover exoplanets. So this is what the Kepler satellite used to discover planets, and the TESS satellite is now using. So the idea is that you are looking at a star, and if a planet passes in front of it, even though you don't see the planet and you don't see the disk of the star because it's so far away, it just looks like a pinprick of light, you can monitor the brightness of the star, and you can see that the brightness of the star dips when the planet transits across the surface. So now imagine that you have a moon orbiting that planet. So the planet's orbiting the star, and then it transits, it goes to across the disk, and the moon is going around the planet. So that would create some asymmetries in the shape of the transit that you would observe, and you could potentially infer the presence of exomoons that way. So smaller things orbiting around planets. Sort of side note is that exomoon is sort of an interesting thing to say. It sounds really cool. These things might as well just be like binary planets. Like we might just find something that has a moon that's the size of Jupiter or something. So what if you have like two planets that are orbiting around each other? So I think that's cool to think about too. Another way that, as far as I know, has not been successful yet, but that people have thought of for trying to detect exomoons or binary planets, depending on whatever you feel like calling them, is playing off of the direct imaging method. So the direct imaging method of looking for planets is exactly what it sounds like. You just point your telescope at a star and you look for planets next to the star. Direct imaging is really hard because planets are really faint, stars are really bright. And so you need a lot of like fancy engineering and also like algorithms to pick out the planet signal from the star signal. And so we haven't been able to use that to see like two planets, but people are developing special algorithms to look for signatures of binary planets or exomoons that way too. So the photometric way, looking for the transit signatures of exomoons, is where the candidates so far have come from, but we might see those or other methods produce other exomoon candidates in the future.
Exomoons, I like it. Then we'll get exocomets, exoasteroids.
We actually have seen exocomets.
Really?
Yeah, this is something that I didn't know.
I didn't know that.
Yeah, I have to credit Ryan Rubenzahl with teaching me this a couple of weeks ago. But yeah, we've seen like spectroscopic signatures of exocomets. So
so in transits, you'd see the lines of the comet?
It's not okay, I don't actually understand it, so I'm going to stop talking about it. But we have seen exocomets. Ask Ryan. He knows.
Okay, so there's evidence for exocomets. All right. I'll have to learn more about that. Learn something every day. Thank you, guys. Here's one that we got online before the presentation began, so we can try and address it. Why do we care? You know, you always read about black holes. Black holes, everybody loves black holes. Why do we care about black holes?
Honestly, I feel the same way because I care way more about neutron stars. And like, they don't even have an appreciable surface. So no.
True.
Yeah. Just kidding though.
So you don't want to, you're on the bandwagon. You're like, who cares about black holes? Neutron stars rule. Black holes rule.
I think, okay, I have a theory. So we will talk about astrophysics. They are pretty cool astrophysically, but I think it's also just that their naming was done so perfectly that it's, it makes for a really good and catchy headline because it catches our imagination. So that is one part of it as well, I think, over the years. But okay, going back to astrophysics.
So Tony, Sarah, why do we care about black holes? Any opinion?
They probe from what I understand, they probe the breakdown of our physics as we understand it. That's part of why the most recent Nobel Prize was awarded to Andrea Ghez, Caltech PhD alumnus, by the way.
That's right.
And now professor at UCLA of astronomy, because she and her team showed independently of Reinhard Genzel that we have a supermassive black hole in the center of our galaxy. And that is where Einstein's general relativity breaks down. If you talk to people who are purely interested in physics, black holes, which astronomer black holes are things that, you can observe things going around them. Physicists construct black holes to really push their equations, and they don't care if they really observe them or not. But for them, it's really the, where quantum field theory breaks down, where you really can't merge the theories of the very, very small and the very, very relativistic.
Yeah, I think that's a good explanation. I would just add that generally scientists aren't involved. Like, sure, it's nice to be able to explain the everyday stuff that we deal with. But once we have an explanation for that and a theory for that holds pretty well, we start probing the edges where things start to break down, as Tony was saying. And so, for instance, Isaac Newton came up with the theory of gravitation, 400 years ago, and that works really well for a lot of things. It works for an apple falling out of a tree. It works for planets in their orbits around the sun, and it does a good job of explaining these things. And we can use this to the benefit of society in a variety of different ways to make predictions about how systems will move in the future. But it's not perfect. And so Einstein's relativity is really just like an adaptation that sits on top of Newton's gravity, that adapts it and behaves like Newton's does for all of those cases where we have an intuition, like how an apple falls out of a tree and how a planet orbits. But in these kind of corner cases, like when you get really, really close to the sun, or when you're traveling really, really, really fast near the speed of light, then it gives a slightly different prediction, which it turns out is more accurate with reality compared to something like Newtonian gravity. So yeah, exactly. I'm just piling on and agreeing with Tony that black holes are one of those corner cases in the universe and in science where things kind of break down and our theories don't really make firm predictions. And so we want to see what is actually going on in those corner cases and come up with a better theory to describe how the world works, how the universe works. Plus, it's cool because you get these weird effects like time dilation, like time slowing down or speeding up, or, or spaghettification, stuff getting stretched out. Nobody wants to be spaghettified, but it's pretty cool. Okay. Questions. Aren't we confident that the actual number of observed exoplanets is greater than 5,000, but the verification process hasn't been completed yet for all of them?
Yeah, so there are a lot more exoplanet candidates than there are confirmed planets. And depending on the method that you use to identify a candidate, there's different processes that go into like actually following it up and confirming it. So an example might be like, it also changes over the mission's lifetime, or the detection method's lifetime, as people learn more about it. So like when Kepler was first launched, if you saw something that like caused a brightness dip from Kepler, there was a lot of follow-up that was involved. Generally, people did like radial velocity follow-up. So they looked at the star speed over time, trying to infer the presence of a planet that way. Or they did ground-based photometry. So they just tried to use another instrument that was on the ground to detect the transit signature. A whole host of other things. They did imaging, looking for potential background stars or other things. So at the beginning, there was a lot more follow-up involved to like getting a Kepler candidate from candidate to bona fide planet. But as people studied Kepler's systematics and light curves more and more, they learned more about like the signatures of potential false positives in the light curves themselves. And so they were able to identify things as bona fide planets just from the light curves. So that's an example, but yeah, so there are more candidates, especially from TESS, which is still in its sort of earlier stage of its life, than there are bona fide planets. but there's still a lot of bona fide planets.
But what about the prediction? I mean, aside from just like the candidates and aside from the ones that we've, confirmed, what about the prediction for how many exoplanets there are, like in the Milky Way? Because it's got to be surely larger than, 4,000 or 5,000, right? How many do we think are out there based on what we've studied so far?
Yeah, so our best occurrence estimate, so that's measure of like on average how many planets each star has, is like pretty much 100%. So like, most stars have planets. So as many stars as there are in the Milky Way, there are at least probably that number of planets.
So like 100 billion planets for the 100 billion stars.
Yeah. There's a really cool visualization that I can try and find of like where in the Milky Way the planets that we found are. And you just like see the sun and it's just like a tiny little like ball around where we are. And there's just like this huge amount of space that we just haven't probed. And it makes sense. Like this is another like selection effect. This is, based on the capabilities of these methods. It's also why the planet that connecting back to before, I told you that the proper motion of the star that I worked on was very high. It had a very high motion because it was so close and it was moving so fast relative to other stars. And that's exactly why. It's because we can only see these tiny changes in the speed of the stars for the closest stars. So all the planets that we've discovered are really nearby in a galactic scale.
But tying back to when we were all talking about the Gaia mission, I mean, Gaia's been able to measure the positions for, instead of just our little neighborhood. If this is our Milky Way galaxy, I don't have another good example. I don't have a disk. I need a record. That would be a good example. If this is the size of our Milky Way galaxy disk, and the sun is like here, we can see what, like a centimeter or something like that, or probably even smaller for scale in terms of the planets around that. But with Gaia, this mission, it's actually measuring a substantial component of the disk of that galaxy and the trajectories of the stars in that region. So hopefully that'll give us an idea of the exoplanets, or these other missions, not just Gaia, but other missions that are measuring, astrometry for a much larger volume. That's super exciting.
I found this visualization I was looking for too.
Share the screen, show it to us.
I love this visualization. So here's the galaxy, our Milky Way galaxy, and we're pretty zoomed in here. And all the known planets are in this little red blob, and then this cone. And that cone is actually Kepler. So Kepler stared at this portion of the sky for a really, really long time. And so since it stared for so long, we know of pretty distant planets because we got good precision, good photometric precision for these stars that were farther away. So this cone is Kepler. These are all of the other photometric and RV and direct imaging discovered planets. And then these ones that are a little bit farther away are microlensing exoplanets. So microlensing is another method that actually works better when there's more background stars. So there's more stars as you look towards the center of the Milky Way. So they're actually more sensitive along this direction.
Oh.
But yeah.
Tony, weren't you saying that you were working on microlensing research now?
That's right. Yeah. That's the new project that I've been getting involved in. And yeah, exactly as Sarah was saying, it's easier to find things when you have more background. And you can see really clearly on that diagram, it's toward the center of the galaxy. And toward the center of the galaxy, you just have higher densities of stars. There's just more stuff there per cubic volume of space.
Are you, in the project that you're starting and looking at microlensing events, are you looking for exoplanets or other? I know microlensing has been used to try and deduce or put constraints on whether or not dark matter was in kind of macroscopic blobs, or how many kind of dark black holes or rogue dark planets are flying through our galaxy, and what sort of stuff are you doing with microlensing?
We're actually, part of it is that we just don't know what we're going to find, because we're going to be looking into the galactic plane, into the disk, not toward the galactic bulge where most people have looked before. So if we find black holes being microlensed, if we find solitary neutron stars being microlensed, those would all be fantastic things. but it's more difficult when you look into the disk, out into the plane of the galaxy, because there are fewer stars. But if we can understand the population of things that are hard to study in there, that could be cool. If we find nothing, that's also very cool, because we know that there's nothing there.
Yeah, non-detections are a constraint as well. It's important to remember that. That's awesome. Okay. Questions, more questions. Could a difference in a planet's orbit be due to a system in physics that is yet undiscovered, such as the search for planet X and how it was actually explained by quantum physics? Now, I'm a bit unclear. Planet X, I thought Planet X was like tied with the whole Nibiru stuff, which has been pretty conclusively kind of shown that it isn't true. I didn't know it was tied to quantum effects, but the question still stands: can a planet's orbital position or orbit be modified by some unknown physics that we don't yet understand? And I mean, I don't know. I'll leave it to the planetary people here, but seems like, yeah, right. There could be some unknown physics that we don't understand that might modify something. Do you want to chime in? You don't want to chime in.
I put my name on the Google Doc, so I will chime in.
Okay.
I did not realize it was Planet X. I thought it said Planet 9. I'm like, okay, yeah, I can. Okay, but Planet X, I can't.
I think the Planet X thing. It's my understanding that Planet X was just a theory that suggested that there was an object in the outer solar system that might have some sort of long period that we haven't observed, which I guess is consistent with the ideas for Planet 9. I actually don't understand a lot of the details of the differences, but it seems like the modern day idea of this is Planet 9, which might not be there, but there seems to be some evidence that suggests it might, and it's definitely an ongoing search for a massive planet in the outer solar system. But please, people, don't worry. It's not going to come crashing into the inner solar system and destroy us like some ancient civilization predicted. We're reasonably sure that this is not a thing. So don't go and sell your house.
I think, well, when I first read this question, I think a good thing to differentiate is between unknown physics and unknown physical mechanisms. As far as unknown physics, I feel like we're very confident that there's no, new quantum hyperdynamics or, very general relativity, something like that, affecting planetary orbits, because we understand things at those scales very well, and we can predict things very well, and current physics does a good job at that. But when I say physical mechanisms, I mean things that the physics that we already know can complicate. So turbulence is a great example. Like, turbulence can arise from just classical physics, but it's very, very difficult to explain anything that arises from turbulence. And I wouldn't call that unknown physics. I'd call that a poorly understood mechanism of physics that we already understand. And I don't know how much this can affect planets when they're in their orbits. I'll leave it up to someone else to answer this. But there are plenty of other examples in astrophysics where that's the case. And part of that is, for example, in things that I've studied before with young stars and star formation. Turbulence is huge and not at all understood in that context, at least. So that's a partial answer to this question, I hope.
Yeah, I think that's good. That's a good explanation. There was a quick question. Hey, Cameron, if our solar system moves in and out of the Sagittarius arm, would that conceivably cause perturbations and ultimately change the hydrodynamics of our planet? So a couple of just quick definitions. The Sagittarius arm is one of the arms in the spiral arms of the Milky Way that we presume exists. Of course, it's difficult to see this because we're in the plane, like I was talking about before, like a record or like a vinyl disc. the plane of the Milky Way is reasonably thin. I mean, that's what you can see when you look out in the night sky and see that glowing disk. We're in that plane, so it's hard to see the individual spiral arms because we're looking through all that stuff at the other arms. I really need to get, I'll have a prop next time of a disk so I can better explain these things. But the spiral arm, yeah, all of the stars that are in the disk of the Milky Way, they aren't just like, some of them I guess maybe, but they aren't just hanging out in that disk all the time in their orbits. Oftentimes they have little perturbations, and that might take them a little bit above the disk and then a little bit below the disk as they do their orbit around the center of the galaxy, kind of like a dolphin jumping out of the water and then dropping back down, and then jumping out of the water and dropping back down. And our solar system is doing that. And even though it takes our solar system, our sun, all the planets, about 250 million years to make one full orbit around the center of the Milky Way. I forget the exact period. I want to say it's about 100 million years that it goes up and it passes through the disk of the central plane of the disk of the galaxy on that kind of time scale. And people in the past have been like, 100 million years, that happens to be the time scale over which we have mass extinctions in the historical record on the Earth. And so it's been suggested in the past that as the solar system goes through the thin disk, like the actual plane of the Milky Way, which is much denser than the other parts of the disk, both dense in terms of lots of stars, as well as dense in terms of gas, that it might, as it's passing through that, it might have some sort of gravitational interaction with the stars that come close to it, that might send off comets that are hanging out in the outer part of the solar system in the Oort cloud. It might perturb them enough that they come crashing into the inner solar system, and maybe they run into the Earth and cause some sort of mass extinction like what knocked off the dinosaurs. I think it's a hypothesis. It's interesting, but I think it's a bit controversial, and it's definitely not like we know the answer, that this is clearly the answer, but it's pretty interesting to think about that there is some alignment in the timescales on this front. But in terms of changing the hydrodynamics of the planet, I mean, the planet, for the most part, like the core of the planet, it's all rock. We aren't worried about how that's going to move that much. It doesn't really behave like a fluid. There are fluids on top that are defined by hydrodynamics in terms of the oceans and in terms of the atmosphere. Those all behave like that. They might get perturbed a little bit when we go through that disk of the Milky Way, but mostly it's going to be objects in orbit around the sun, like the planets, or as I said, comets or asteroids, which might get perturbed as they go through this disk. But yeah, hopefully that answers some of the question. Okay, another question. Here's a good planet. How do we find an exoplanet which is tidally locked with a star?
This is a cool question because it's actually one of the easiest types of planets to find. We think that the first exoplanets to be discovered orbiting sun-like stars are most probably tidally locked. This is the class of hot Jupiter planets that I mentioned briefly in my talk. So these are big giant planets that are more massive than Jupiter, that are very, very close to their star. So they have orbits of a few days sometimes. So the first exoplanet to be discovered around a sun-like star, like not a pulsar, was one of these hot Jupiter exoplanets. And we think that it's slightly controversial, but people think that hot Jupiter planets are tidally locked. So the same face of the planet always faces the star. Just the way that we always see the same face of the moon. The moon is tidally locked to the Earth. We believe that we theorize that these hot Jupiter planets are also tidally locked and on very circular orbits.
Yeah, that's great. That's a good explanation. How many objects do we know in the solar system that are tidally locked, like the moon is locked to the Earth? I guess in the long-term behavior of the moon-Earth system, eventually the Earth will be tidally locked to the moon. So only you can only be like, let's say the moon would be stuck on the side facing North America. That means every night you'd look up in the sky from North America and you'd be like, oh, full moon tonight again. Or if you were in Russia, you'd look up and be like, no moon tonight again. But that's a ways in the future. So, but are there other objects? Do we know of a lot of the planets that are on? I know there's a lot of resonances with between the orbits of different planets, and Mercury, I think, is tidally locked with the sun, right?
3-2 spin orbit resonance. So it's not exactly tidally locked, but it is the spin and the orbit are in resonance. So it's not that it spins once for every time that it goes around, it's that it spins 1.5 times for every time that it goes around.
What about, do we know Venus? I mean, obviously this is going to be the closer into the sun, the more strong the gravitational influence is. And so it's going to have this locking effect preferentially in the inner part of the solar system. But is this true for Venus as well? I don't think it is, but I trust you planetary people to.
I don't know why.
I guess we need a solar system person in here.
Yeah, I'm 99% sure Venus is not tidally locked.
Yeah.
Yeah.
Right. Venus rotates the other way. That's right.
Right. Yeah.
It's a weird one.
Yeah. So hot Jupiter planets are actually like within the orbit of Mercury. So they're closer to their stars than Mercury is to our sun.
That's pretty.
You need to be really massive and really close to be tidally locked. So there might be moons in our planet that are tidally locked to their planets, but I don't think any of the planets are tidally locked to the sun.
Okay. Here's a recent question. How difficult is it to get telescope time to conduct your research? That is a good question. And I'm sure, well, I don't use telescopes so much anymore. I do computer modeling, so I just have to apply for supercomputer time, and it's a pain, but yeah, you can usually get it. But with telescope time, do you guys want to, I guess, yeah, Sarah, Amruta?
So this is the story of my life. This is what I do most of the time is, ask people to give me time on different telescope. That comes with being a multi-wavelength observational astronomer, because I do like optical, X-ray, gamma ray, radio, like all of them. And so what I've learned is it depends on what telescope you're applying for, the difficulty goes up. So for example, Hubble Space Telescope is extremely oversubscribed. And applying for Hubble Space Telescope time is almost like throwing pennies in wishing wells. That's what I think. I did luck out once, so that was really fun. But if you're looking at smaller telescopes run by, smaller optical telescope, for example, the telescope that we have at, the Palomar Mountains, with Caltech having a pretty good access to these, I think it gets relatively easier to get time on those, but it's just that we have a lot more cool objects and a lot more astronomers, and compared to that, way lesser telescopes and telescope time. So everything is an oversubscription. So, yeah.
Yeah, I know so just to make sure everyone in the audience knows, so telescopes, usually you have to apply for, you have to propose a science project, because, I don't have my own personal space telescope. Maybe if you're Elon Musk or something, or some wealthy person, you can have your own personal space telescope. But most people don't have the instruments to themselves because they're quite expensive. So either NASA or the National Science Foundation or these major consortia of different universities will build these things together and then dole out the usage of that to the people who work in their institutions. And yeah, with Hubble, anyone can apply for Hubble Space Telescope time, even you sitting at your on your couch in your robe right now in your slippies, you could type up a nice little proposal and be able to look at your favorite object. But what you have to do is provide a good science justification case for why they should give you like one night, or I don't know, 90 minutes, a single orbit to look at that object over there, and that you're going to be able to do some awesome science if they give you that time. And then there are committees made up of scientists like those of us here today, who will review the various different proposals and be like, oh, this person wants to do this this cool thing, and they only require, one orbit of time on Hubble to be able to do this, and they're going to revolutionize our field with the science. Let's give it to them. And so then you'd get this. But with Hubble, yeah, it's like a 10-to-1 ratio of proposals to actual time. So you get, 10% chance, assuming everything is equal, which it's not, but assuming everything's equal, you have a 10% chance of getting this time. Yeah, I guess I was kind of, only one orbit of Hubble is 90 minutes of time on Hubble is a big deal. So
yeah, I was just thinking one whole night with Hubble.
One whole night of Hubble. That's right.
Here, that's literally $1 million.
Yeah.
Yeah. So one good way to think about it is that 1 second on a space telescope would cost you about $1,000 to keep it operational and to observe something and to get that data downlinked and pay people to make it all work together and avoid sun angles, avoid other things ramming into telescopes, etc. So you have to start if you think of it that way, it's really expensive to keep these telescopes afloat and to keep them running. So that's why, and there's only so much time in a year that you can look at things, right? So, yeah.
Sarah or Tony, do you guys want to chime in?
Sure. I mean, I guess one thing I can add is just that institutions buy into different telescopes, and there's an extremely unequal allocation of time on big telescopes among institutions. So Caltech has a lot of time on big telescopes. Like Caltech has a lot of time on the Keck telescope, for example. So it's just something to keep in mind too. Like astronomers at Caltech have a lot more access to telescopes and observing resources in general than pretty much anywhere else. Which I say not to brag, but just to sort of highlight disparity.
Yeah, there is definitely disparity because of the wealth of the institutions and
the wealth of the nations as well. So
absolutely.
Yeah.
And if I can chime into a nice comment I saw in the chat, Physics Police says, my backyard telescope is somewhat undersubscribed. And you know what? Amateur astronomers have made contributions to professional astronomy that are very significant. And yeah, if you want to use your own backyard telescope and observe things, you can join various professional societies. I've looked at light curves from the American Association of Variable Star Observers, and that's great because that compiles sort of all of the people, all the amateur astronomers who I think are subscribed to that or they're members of it. I don't know exactly how it works, but amateurs have found comets I forget what it's called, Comet Lovejoy or something, were found by this guy in Australia who just had a lot of time to kill. And yeah, if you're willing to do it yourself, you can have all the telescope time in the world you want,
Absolutely.
You might even discover a thing or two.
Yeah, and actually, so adding to Tony's point, so some of these things that I study, I was talking earlier about, things going into outburst and getting extremely luminous in space, wherein, there is a sudden enhancement of flux. And sometimes these things, even with backyard telescopes, you can see this brightening. So for example, one of the systems that I study, we track it with really sophisticated instrument to see, if it's, going into an outburst or not. But there was an amateur astronomer working with AAVSO who actually was building up the light curve. And now if you go back to that AAVSO light curve, you can just see there is this direct jump into the optical flux wherein you can see that the state transition with this kind of an extreme outburst violent event has happened. And it's really useful. So I do from time to time actually go look up at AAVSO light curves as well. So yeah.
Nice. Yeah. So citizen science matters. So
it matters a lot.
To things like AAVSO, the variable star observations that Tony was referring to and Amruta were referring to, or various different other methods. So we definitely appreciate it. Unfortunately, that brings us to the end of the night. Thank you to Sarah, wonderful presentation and subsequent discussion. Thank you to the other panelists, Tony and Amruta. Wonderful. I really enjoyed the conversation and I learned stuff tonight about like exocomets. Super cool. So thanks out to our audience. We will have another one of these in a month. I'll advertise it on our both on our YouTube as well as our social media and our website. And we will have a week from Monday, we will have our astronomy on tap. I've already got one speaker. I think I have a second speaker. It's going to be awesome. So definitely check it out. And we'll have beers and pub trivia because everybody likes pub trivia. And yeah, stay safe, everybody. Thanks a lot.
Thanks, Cameron.